Hey there, science fans! Have you ever wondered why a straw in a glass of water looks broken? It's not magic, but a fascinating trick of light called refraction. When light passes from one medium to another, like air to water, it bends. This bending causes the straw to appear disjointed at the waterline. Or why diamonds sparkle so brilliantly. The secret lies in how light interacts with the diamond's internal structure. As light enters the diamond, it bends and bounces around inside, creating that mesmerizing sparkle we all love. These everyday phenomena are all thanks to the fascinating way light behaves as it travels through different materials. Whether it's glass, water, or even air, light changes direction and speed, leading to a variety of visual effects. It's all about bending and bouncing. When light hits a surface or passes through a medium, it can either bend, known as refraction, or bounce back, known as reflection. These principles are at the heart of many optical phenomena. Today we're going to dive into the science behind this phenomenon with Snell's law. Named after the Dutch mathematician Willebroord Snellius, Snell's law describes how light bends when it enters a different medium. It's a fundamental principle in optics. Get ready to unlock the secrets of light. Understanding Snell's law not only explains why objects appear bent or sparkling but also opens up a world of technological applications. This bending of light isn't just a cool trick, it plays a crucial role in how we see the world around us. From the way we perceive objects underwater to the design of lenses in our glasses, refraction is everywhere. From eyeglasses to fiber optics, Snell's law governs the behavior of light in countless applications. Eyeglasses correct our vision by bending light to focus it properly on our retinas, while fiber optics use light to transmit data over long distances with minimal loss. So, put on your thinking caps, and let's shed some light on Snell's law. By understanding this fundamental principle, we can appreciate the beauty and utility of light in our everyday lives. Whether it's the sparkle of a diamond or the clarity of our vision, Snell's law is at work, making the world a brighter place. Snell's law describes how light bends when it passes from one medium to another, like from air to water. This bending of light is known as refraction, and it occurs because light travels at different speeds in different materials. When light enters a new medium at an angle, its speed changes, causing it to change direction. It's all about the angles. The angle at which light hits the surface of the new medium and the angle at which it bends are crucial to understanding Snell's law. Here's the equation: n1 synth 1 equals sine n2 synth 2. This equation helps us quantify the relationship between the angles and the refractive indices of the two media. Now let's break it down. Each part of this equation has a specific meaning and role in determining how light will behave as it moves from one medium to another. N1 is the refractive index of the first medium, like air. The refractive index is a number that describes how fast light travels in that medium. The 1, theta 1, is the angle of incidence, the angle at which light hits the surface. This angle is measured from the normal, an imaginary line perpendicular to the surface at the point of incidence. N2 is the refractive index of the second medium, like water. Different materials have different refractive indices, which affect how much the light will bend. Theta 2, is the angle of refraction, the angle at which light bends after entering the second medium. This angle is also measured from the normal. The refractive index is a measure of how much a material can bend light. Materials with higher refractive indices bend light more than those with lower refractive indices. The higher the refractive index, the slower light travels in that material and the more it bends. This is why light bends more when it enters materials like glass or water compared to when it travels through air. Understanding Snell's law is essential for fields like optics, physics, and even photography, as it helps us predict and manipulate the behavior of light. Imagine shining a flashlight into a pool. What happens to the light beam? That's right, it changes direction. This bending of light is called refraction. Here's the catch. The amount of bending depends on the density of the materials. Light travels slower in denser materials like water than in less dense materials like air. Pop quiz. If light travels from a less dense medium like air to a denser medium like water, will it bend towards or away from the normal line, the imaginary line perpendicular to the surface? Think about it and we'll reveal the answer in the next section. Let's put our knowledge to the test with an example. Snell's law is a fundamental principle in optics that describes how light bends when it passes from one medium to another. This bending of light is called refraction, and it occurs because light travels at different speeds in different materials. By understanding Snell's law, we can predict the path of light as it moves between substances like air, water, and glass. Imagine a ray of light traveling from air, N1 equals sign 1.00, to water, N2 equals sign 1.33, at an angle of incidence, B1, of 30 degrees. The angle of incidence is the angle between the incoming light ray and the normal line, which is an imaginary line perpendicular to the surface at the point of contact. What is the angle of refraction? V2. The angle of refraction is the angle between the refracted light ray and the normal line. To find this angle, we need to use Snell's law, which relates the angles of incidence and refraction to the refractive indices of the two media. Remember our equation, N1 sin 1 equals sign N2 sin 2. Here, N1 and N2 are the refractive indices of air and water, respectively, and Th1 and Th2 are the angles of incidence and refraction. Plug in the values, 1.00 sin 30 degrees equals sign 1.33 sin 32. The sine of 30 degrees is 0.5, so we can rewrite the equation as 1.00 0.5 equals sign 1.33 sin 32. 2, solve for sin 32, sin 32 equals sign 1.00 times 0.5, divided by 1.33, which is approximately 0.376. This step involves simple division, but it's crucial to ensure accuracy in your calculations. 3. Find 2 the 2 equals sign sin 1, 0.376, which is approximately 22.1 degrees. The inverse sine function, also known as arcsine, helps us find the angle whose sine is 0.376. So, the angle of refraction is approximately 22.1 degrees. This means that when light enters water from air at an angle of 30 degrees, it bends and travels at an angle of about 22.1 degrees relative to the normal line. This means the light bends towards the normal line as it enters the water. The bending occurs because light slows down when it moves from a less dense medium like air to a denser medium like water. Remember our pop quiz? You got it. Understanding how light behaves at the boundary between different media is essential in fields like optics, physics, and even photography. Light bends towards the normal when moving from a less dense to a denser medium. This principle is not only fascinating but also has practical applications in designing lenses, glasses, and various optical instruments. Section 5. Snell's Law in Action. Snell's Law isn't just for textbooks and labs, it's at play all around us. Ever noticed how objects underwater appear closer and slightly distorted? That's because light bends as it travels from water to our eyes. Diamonds and other gemstones sparkle because of how they refract light. Their cut is designed to maximize this effect, bouncing light around inside the gem. These thin glass fibers transmit data at lightning speed using total internal reflection, a cool phenomenon we'll explore next. Snell's law is the backbone of this technology, allowing light to travel along the fiber without escaping. Section 6. Total internal reflection, a light trap. Sometimes light gets trapped inside a medium. This happens when light traveling from a denser medium to a less dense medium hits the boundary at a steep angle. Instead of refracting, it reflects back into the denser medium. That's total internal reflection. Imagine shining a flashlight into a pool from underwater. If you point the light straight up, it will refract out of the water. But if you tilt the flashlight, increasing the angle of incidence, you'll reach a point where the light reflects back into the water. This phenomenon is crucial for fiber optics, keeping light signals confined within the fiber and allowing for long-distance, high-speed data transmission. Section 7. The critical angle, a balancing act. The critical angle is the angle of incidence at which the angle of refraction becomes 90 degrees. It's the point of no return. If the angle of incidence is less than the critical angle, light refracts. If it's equal to or greater, total internal reflection occurs. It's like a delicate balancing act between refraction and reflection. Think about our flashlight in the pool again. The angle at which the light transitions from refracting out of the water to reflecting back in is the critical angle. Section 8. Snell's Law Quiz. Test your knowledge. Ready to test your understanding of Snell's Law? Here's a fun quiz. 1. What happens to the speed of light as it travels from air to glass? A. Increases. B. Decreases. C. Stays the same. 2. What is the critical angle? 3. Give one example of how Snell's law is used in real life. Answers. 1. B. Decreases. 2. the angle of incidence at which the angle of refraction is 90 degrees. 3. Fiber optics, underwater vision, gemstones. Section 9. Conclusion, the wonders of light. From rainbows in the sky to the sparkle of a diamond, Snell's law governs the captivating behavior of light. Understanding this simple law unlocks a world of optical wonders, revealing the science behind everyday phenomena and cutting-edge technologies. So keep exploring, keep questioning, and keep the spark of scientific curiosity alive.